All right, good morning. This is Monday, November 9th, 2020. This is CP Physics, and today's notes are on one-dimensional elastic collisions. Pretty exciting stuff. One-dimensional elastic collisions. First of all, in physics, momentum is always conserved. Momentum is always conserved. Whatever is going on before, written here is the vector sum of all the forces acting on something before, that is equal to the sum of all the momentum, I said forces, all the momenta before a collision is equal to the sum of all the momenta after a collision. And a collision or an explosion is the same thing. Then last week, I pointed out that there are three types of collisions. In a perfectly inelastic collision, everything sticks together like Velcro. In fact, since I happen to be in the science building today, I could have tried to find the little physical objects we have that are examples of this. We have happy balls and we have sad balls. When you drop a sad ball, it just sticks to the floor. When you drop a happy ball, it bounces off the floor. The other extreme is to call it a perfectly elastic collision. And here they bounce. And what's more important is that if it's perfectly elastic, that means kinetic energy, the sum of all the kinetic energy before they collide is equal to the sum of all the kinetic energy after they bounce off of each other, which is more math. And then in between these two extremes is much of the real world, which are just elastic collisions, but they're not perfect. This is a basketball. It bounces, but it doesn't return to its starting height. Same for a tennis ball, golf ball, football, baseball, super ball. Any object you want to drop and bounce, it tends not to return to its starting height unless you give it some additional energy to restore what it loses when it hits something. And some of you guys are throwing things now just to demonstrate elastic collisions. Okay, nice. Now, we're going to do three killer situations. I'm actually doing this from some notes called one-dimensional elastic collision notes. I don't remember if I happen to schedule this to be released to you right now. You know, that's possible. Might be on our Google Classroom. I don't remember. But I'm going to work through these examples. So, example one, I have two billiard balls. Which I'll just draw as a circle and remind you that billiards means shooting pool. They are considered to be identical in mass. So the first one is considered to be going at 3 meters per second to the right. The second billiard ball, so I'm going to draw it same size, starts off moving 1 meter per second to the left. These things are going to collide. Now, what kind of collision is it going to be? This is going to be a one-dimensional head-on collision. And I'm going to declare it to be perfectly elastic. Okay, a one-dimensional, perfectly elastic head-on collision. And the question is, if this is ball A and this is ball B, and initially ball A is going 3 meters per second to the right, and initially ball B is going 1 meter per second to the left, what are their final velocities after they bounce off of each other? The answer in this special case is trivial, but the math to prove it to you is brutal. And since I love math and you love math, let's do the brutal math. Ni hao, welcome back. The brutal math says the sum of all the momentum before they collide is equal to the sum of all the momentum after they collide. Notice I haven't given you the mass of the billiard balls yet. That's because in this special case, the two masses are identical. And because they are identical, it does not matter what their mass actually is. It could be a gram, a kilogram, a megagram, a gigagram, or 2 grams. It's going to not matter. To keep you poor physics students slightly happy, I will assign a value of 1, okay? So let's just pretend mass 1 equals mass 2 equals 1 kilogram so that you don't freak out too badly. Okay. Now, if it was actually 5 kilograms, it makes no difference. That's my point. Here we go. So what is the momentum before they collide? That would be 3. Okay, I remind you, momentum is mass times velocity. And fortunately, I chose 1 for my made-up mass. So momentum 1 is 3 kilogram meters per second. We have 3 kilogram meters per second. 1 meter per second to the left means minus 1 kilogram meter per second. 3 minus 1 means the total momentum before they collide is 2 kilogram meters per second to the right. After they bounce off of each other, the total still has to add up to 2 kilogram meters per second. But right now, there's an infinite number of combinations I can use to come up with that. I could say the first ball stops and the second ball has that much. I could say the first ball bounces completely, the second ball stops. I can, I don't have enough information to settle what are their final velocities. And maybe I need some sort of labeling here, right? So for ball A, after it bounces, let's presume that it's going to go to the left. For ball B, after it bounces, let's presume for now that it's going to go to the right. We don't really know for sure, but it's a good starting guess. So I'll call the one on the left VA final, and the one on the right VB final. So those are the two mystery things that we're going to try to figure out. You give me a value of 1, I can tell you the value of the other because the two of them together have to add up to 2. All right. But we're going to claim that this is a perfectly elastic collision. So here comes our new piece of math information. The sum of all the kinetic energy before they collide has to equal all the kinetic energy after they bounce off of each other. Kinetic energy is given by the formula 1/2 mass velocity squared, 1/2 mv squared. I chose a mass of 1 kilogram, but let's see what's going on here. So for ball A, 1/2 times 1 times 3 squared, oh boy, that is 1/2 times 9 joules. For ball 2, it's 1/2 times 1 times -1 squared, which is 1 joules. 1/2 times 9 joules plus 1/2 times 1 joule is 1/2 times 10 joules. So I have 5 joules of kinetic energy before they hit each other. Because this is perfectly elastic, this is how much kinetic energy they're going to have after they bounce off of each other. Oh man. So that means 1/2 times 1 times VA final squared, which I don't know the value of it, plus 1/2 times 1 times VB final squared. Together, they have to add up to 5 joules of kinetic energy. I think I just threw a lot at you for an early Monday morning, so let me pause for a moment while you digest this. I personally don't really care for this 1/2 being there all the time. I'd like to get rid of it. I'm going to multiply everything by 2. The left becomes VA final squared plus VB final squared equals 10. And I'll say joules. Okay, 10. This is one equation, but it has 2 unknowns. It's from kinetic energy. From momentum, I didn't write it down. From momentum, 1 times VA final, so VA final, plus 1 times VB final. And Eva, I'm not sure if I'm going to make a mistake right now. Correct me if I do. Should I have VA final or VB final be negative? Because I said, this thing, maybe it's going to bounce to the left. Yeah. How about if I put it with a minus sign, just because we think it's going to be? So minus VA final plus VB final still has to add up to 2. So that is from conservation of momentum. This is from conservation of kinetic energy. Now I have 2 equations and 2 unknowns. You can solve this by graphing. You can solve this by substitution. You can solve this by elimination. You can solve this by writing it in matrix form and taking the inverse Gaussian, which you probably never learned how to do. You can solve this by converting it to polar coordinates and doing it that way. You can solve this by entering it into your graphing calculator and asking it to find the intersection. Anyone want me to show you how to do that? None of you are that curious, huh? Oh man. I mean, that's a fun way. Look, this is the equation of an ellipse. So ellipses might look like that. This is the equation of a straight line with a negative slope and a y-intercept. So maybe something like that. Maybe above, maybe below the axis. The point is, there's going to be two solutions. And I guarantee you, one of the two solutions will be that they miss each other, or if you like, that they have not yet hit each other. That will always be one of the two solutions. And the second solution will be after they've hit each other. So one solution, maybe like this one, is before, and the other one is after. But so much for doing it graphically. I'm going to do this algebraically. So I'm going to write it again on this fresh piece of paper. What's my current situation? Negative VA final plus VB final equals 2. And then VA final squared plus VB final squared equals 10. Two equations, two unknowns. I'm going to solve this by substitution. I could solve for VB final if I were to add VA final to both sides. That would make this thing look like VB final equals VA final plus 2. So I'll take that and I'll put it in, whoops, I'll put it in here. I'll replace VB final with that expression. Okay, so that makes this thing become VA final squared plus, open parentheses, because you guys aren't going to goof on exponents, are you? And instead of writing VB final squared, we're going to write open parentheses, VA final plus 2.0 close parentheses squared equals 2. Now I have one equation and one unknown. I choose to FOIL the term in parentheses. FOIL means multiply the first two, the outer two, the inner two, the last two. And you're right. I made a math mistake and I'm going to have, that's why I hired Eva to correct me when I make mistakes. Thank you, Eva. Yep, that's supposed to be equal to 10, not equal to 2. All right. Resuming my attempt at doing this correctly, VA final squared plus VA final squared plus 2 times VA final plus VA final times 2. Well, 2 plus 2 is 4 VA final plus 2 times 2 is 4 equals 10. You guys took math. This is a quadratic equation. You love the quadratic equation. You combine like terms and simplify. Let's see. Combine like terms. VA final squared plus VA final squared is 2 VA final squared. This guy is the only one of that type. So plus 4 VA final. I can subtract 4 from both sides, and that makes this thing equal to 6. Now, I remember that the quadratic formula is written in standard form, everything set equal to 0. So how about if I subtract 10 from both sides? That makes this thing minus 6 equals 0. Now, some of you whiz kids can actually factor this one in your head. I look at the 2, the 4, and the minus 6, and I say, hey, those are all even numbers. I would actually prefer to divide everything by 2 first and say, if I divide everything by 2, this would be VA final squared plus 2VA final minus 3 equals 0. Now, think of x squared plus 2x minus 3. And in math 2, maybe in math 1, you're asked, well, factor that. Can you factor this one in your head? Anyone? Something whose product is negative 3, whose sum is positive 2. And I'm guessing if I were to bother to look in the chat, I would see that a bunch of you are giving answers. Okay, so I'm seeing x plus 3 and an x minus 1 from students in the chat. That gives us an x squared plus 2x minus 3 equals 0. Now this x is actually VA final. So VA final equals, the term in parentheses is 0 when VA final is negative 3. So one of the roots is negative 3. The other root is positive 1. In the original problem, before they collided, VA initial was 3 meters per second. So as I suggested, one of the two possible solutions will always be the original value. Oh man, why do I have a minus sign? Oh, I'll blame Eva. Eva, you didn't keep me from goofing somehow down the road. But let's see what I can salvage here. So minus 3, then plus 1. Somewhere I feel like I switched minus signs. Somewhere I made a mistake. I'll write oops, because I believe the answer should be positive 3 and negative 1. So I think I made a mistake someplace because one of the roots is always the original value, not the opposite of the original value. The original value. I'm going to carry on as if I didn't screw up and say, look, here's the two roots for ball A, two solutions. The plus 3 would be what would happen if it never hit the other ball yet? Well, it's still going to the right at 3 meters per second. Maybe it missed it. Maybe it hasn't gotten to it yet. We're not interested in that solution. We're interested in the other case. So VA final is negative 1 meter per second. I claim this is what ball A does after they collide. And I can now plug that into the momentum equation and solve for VB final. So what have I got? Negative 1 plus VB final have to add up to 2. That means VB final is 3 kilogram meters per second. Now I divide it by 1 and I get 3 meters per second as my final velocity. What you might finally notice is the only thing that happened after all this math, if only I hadn't screwed up, is that the two balls swapped their velocities. Ball A was going 3 to the right, ball B was going 1 to the left. Afterwards, ball B was going 3 to the right, and ball A was going 1 to the left. This is a special case. Must have identical masses, must be perfectly elastic. So if they have identical masses, I'm sorry, poking these buttons doesn't make it work out so well, does it? Okay, if they have identical masses and is perfectly elastic, then they swap velocities. By the way, head-on collision. I guess that's a third condition. It has to be a head-on collision, one-dimensional. I thought about proving it to you because I happened to be in the science building this morning. And normally I pull out lab carts and put bricks on them and run them into each other. And you could see with your own eyes that when a lab cart runs into an equal mass lab cart, the first one stops and the second one goes. You may have seen that shooting pool. You have a billiard ball and you shoot it and it hits another ball head on. The first one, so let's make this one like that. The first one stops and the second one goes off with the original velocity of the first one. The cue ball directly hitting any other billiard ball head on, the cue ball will stop completely and the ball that you hit goes straight forward with the speed that it was hit. We also demonstrate this with our Newton's cradle, where I have this thing of two, three, four, five balls all hanging on a string, and I pull one back and I let go. What happens? One hits here, one comes up there. If I pull two of them back, two go that way. Pull three back, three go this way. In every case, it's a perfectly elastic collision, and the number of balls swinging down and hitting is equal to the number of balls going up and hitting. I think break is about to start. I'll see if I can go find that demonstration and show it to you after our break. We have just done 35 minutes of painful math for one math problem that has a trivial solution if they happen to be identical masses, perfectly elastic, one-dimensional collision. The math will always work out this way in this special case. So if I have a red ball going this way and a blue ball going that way, and this one's going at 30 miles per hour, and this one's going at 5 miles per hour, and they have a perfectly elastic collision, then afterwards, this guy will only be going 5 miles per hour, and this guy will be going 30 miles per hour. As long as they're identical masses, one-dimensional, perfectly elastic, they always just exchange their velocities, whatever they were. If one was going 5 miles per hour to the left, then afterwards the other one will be going 5 miles per hour to the left. They always exchange only in this special case. And Kevin, I made a math mistake someplace. Eva didn't correct me this time because, well, maybe she likes watching me fail publicly. I'm not sure. Oh man, there's our 3-minute break. You guys go find my mistake over the next 3 minutes. Da, 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 da. Okay, so then I plugged negative, this would be positive. Good. Someone figured out where I messed up. I suspect I was trying to figure it out during our 3-minute break. Oh, wait a second. I got my earbuds unconnected from my human body. Oh, great. Now, if you say something, I can hear it. So I'm wondering if I made my mistake when I declared negative a plus b equals 2. Maybe I should have declared a plus b equals 2 and then gone forward from there. So that might be where I made my mistake. Let's just hope I don't make it again on the next one. But first, I found the little demonstration thing. So if I disconnect this and go like that, there. You guys may have seen this before, called Newton's Cradle. And I have to figure out where the camera is. Yeah, we're in my classroom. Yes, I know it's out of focus. Oops. There, in focus. Telescopes, the clock, stuff, Newton's cradle. Okay, so with Newton's cradle, the idea is momentum and kinetic energy are kind of conserved. If I were to take one of these balls and let it swing, this is how you students entertain yourself endlessly. Now there's friction, so because of friction, this thing is going to die out, dampen out. But for first approximation, one ball hitting these other four bounces perfectly off of it. And by conservation of momentum, one ball in, one ball out. Two balls in, two balls out. Three balls in, three balls out. 4 balls in, 4 balls out. And as if it weren't too obvious, 5 balls in, 5 balls out. Ta-da! Yes, physics at work, children. Physics at work. Okay, too bad I screwed up on the math that goes with that, but that is physical verification that what I'm trying to have you do isn't really unreasonably wrong. It's just my math skills might be a little bit off. On this handout, there's a second situation. Maybe I'll get this one correct. In the second situation, I have a cannonball. And this cannonball has a mass of 20 kilograms. And it is at rest. But along comes a golf ball. This golf ball has a mass of 1 kilogram and it's moving at 10 meters per second. What are the velocities of each of these two objects after they undergo a perfectly elastic collision? In the previous example, I used A and B. So maybe I should continue on. I'll call this one C, and I'll call this one D. So you don't mix the values with the previous example. And for some reason now, I was unable to zoom in. I don't understand what I do that screws things up. Whatever it is, yes, you mean like this. Okay, maybe I shouldn't fail you then. Oh, too late. What if I go back to video mode? Does it stay zoomed in? Kind of looks like it. I can't tell. All right, let me get on with trying to teach. Huh. First, momentum is conserved. Oh, and this is, of course, before and afterwards. Hmm. I guess we'll just call it VC final and VD final. Let's see what happens this time. So conservation of momentum says, momentum is mass times velocity. For this guy, it is 1 times 10 is 10 kilogram meters per second. 20 times 0 is 0. 10 plus 0 is 10 kilogram meters per second is the total momentum in this problem. And that has to be equal to 1 kilogram times VC final plus 20 kilograms times VD final. So there's my one equation. If I write it without units and everything else, it looks like 10 equals VCF plus 20 VDF. So there's one equation based on conservation momentum where I'm stripping it of its units so that you can just see the bare algebra problem underneath it. Based on conservation of kinetic energy, I have 1/2 times 1 kilogram times 10 meters per second squared plus 1/2 times 20 kilograms times 0 meters per second squared. So that works out to be 50 joules. 1/2 times 1 times 100 is 50. This is just 0. So this is the sum of all the kinetic energy before the collision, and that has to equal the sum of the kinetic energy after the collision. So 50, and I'm going to just write it naked without units, is equal to 1/2 times 1 times VC final squared plus 1/2 times 20 times VD final squared. I still don't really care for that 1/2 all the time. So I'm going to choose to multiply everything by 2 just so I don't have that fraction staring at me. So I have 100 equals VC final squared plus 20 VD final squared. Again, I multiplied everything by 2 because I didn't really want to have that fraction sitting there. So now, based on kinetic energy, I have an equation. Based on momentum, I have an equation. I have two equations, two unknowns, and now, same math skill. Oh, Swetha, that's because Eva is persuading you to just eat and drink in class. Okay, I'm going to substitute one for the other and hope I don't screw up like I did earlier. This time, I'll say VC final is equal to, how about if I try 10 minus 20 VD final? And then substitute that in for VC final. All right, here comes the math. 100 equals, open parentheses, 10 minus 20 VD final, close parentheses, quantity squared, plus 20 VD final squared. I'm going to do FOIL to try to get rid of these parentheses. That makes this thing 100 equals 100 minus 200 minus another 200, so that's minus 400 VD final, plus, now negative 20 times negative 20 is positive 400 VD final squared, plus 20 VD final squared. All right, that looks exciting. I would say I could divide everything by 20. I can also subtract 100 from both sides. Wow. Those are canceling. By the way, Eva failed to correct me from making my other mistakes. You students should stop me from making my current mistakes when I make them. So right now, I have something where I could divide everything by 20. Let's try that. Negative 400 divided by 20 is negative 20 VD final. 400 divided by 20 is 20. 20 divided by 20 is 1. So this is plus 21 VD final squared equals 0. you can factor out a VD final. VD final, open parentheses, 21 VD final minus 20, close parentheses, equals 0. Kids, why do I think I made a math mistake again? I just feel like I did. However, where are we at? When VD final is equal to 0, that would be one of the roots. Well, VD was 0 at the beginning of the problem. So I did not make a mistake. Okay. One of the two roots will always be the original value. The original value for the cannonball was 0. So one of the roots for the cannonball is 0. Ta-da! Now the other root, the second root, is when this term in parentheses is equal to 0. And this will be equal to 0 when VD is equal to 20 divided by 21 as a positive number. Okay, I claim that's the correct value. 20 over 21. Meaning the cannonball will lumber off at a little bit less than 1 meter per second. What about the golf ball that hit it? Well, we said by conservation of momentum, by momentum, 10 equals VC final plus 20 times what will now be 20 divided by 21. Oh man. So 10 equals VC final plus whatever 400 divided by 21 is, right? Okay, well, 400 divided by 21 is 19. 10, and by the way, this is correct. 10 equals VC final plus 19. And it's actually 19.05 if you care. Here, I'll do it that far out. Too many sig figs, Eva says, but so now if I subtract 19.05 from both sides, I have VC final is equal to negative 9.05 meters per second. That's the final speed of the golf ball. The final speed of the cannonball is 20 divided by 21 is 0.95 2 meters per second. Here's the punchline. When a little teeny tiny object has a perfectly elastic collision with a big object, the little teeny tiny object bounces almost with the same speed that it hit it. while the big object scarcely moves. It lumbers along. The algebra that I did this time is correct. Unfortunately for you, there are 3 examples on this handout, and we've only done the first 2. And I want to do the third one as well. Good thing we're recording this, right? You'll be able to play this back and say, oh, that's what he did wrong. Example 3. It says, now I have a massive ball moving that hits a little ball that's at rest. Eva, should I use the numbers that are on the handout, or should I make up numbers? Okay. On the handout it says, I have a 3 kilogram mass, and it's going at 4 meters per second, and it hits a 1 kilogram mass that is initially at rest. This is, just like the other 2, perfectly elastic, which is the only way we can solve this problem, unless they give us additional information. And the question is, so great, if this is A, B, C, D, if this is E, and this is F, what is the final velocity of E? What is the final velocity of F after this massive ball hits this little ball? If you've ever played sports and you happen to have a tennis ball and a basketball, you can demonstrate the result at home. Put the tennis ball on top of the basketball and then drop the basketball with the tennis ball following it down to the ground. You will see the result that matches the horrible math we're now going to do. The horrible math is exactly the same as before. So we have conservation of momentum that says 3 kilograms times 4 meters per second plus 0 is 12 kilogram meters per second. That's the total momentum. That's the total momentum after they collide as well, which is going to be 3 times VE final plus 1 times VF final. So here's one equation. I'll write it naked. It looks like 12 equals 3VEF plus VFF. I'm writing it without units, without sig figs. So you could look at this as if it were a X and Y math problem. Separately, for kinetic energy, 1/2 times 3 times 4 meters per second squared plus 0 equals, oh man, 16 times 3 is 48. I'm going to write this as 1/2 times 48 joules, because you know I'm going to try to get rid of that 1/2 later anyways, is equal to 1/2 times 3 times VE final squared plus 1/2 times 1 times VF final squared. Now, if you students are better than I am, I will try to catch up to you. You can just go ahead and solve this now, all on your own. Meanwhile, I'll try to catch up to you. So what have I got? 48, 1/2 times 48 is 1/2 times 3VE final squared plus 1/2 VF final squared. I hate that 1/2. I'm going to multiply everything by 2. I now have 2 equations, 2 unknowns. I'm going to substitute for one into the other. I guess I will do VF final equals 12 minus 3VE final, and put that in for VF final. Huh. So I did FOIL. If I didn't make a mistake, I'm already at the line that says 48 equals 3 VE final squared plus 144 minus 72 VE final plus 9 VE final squared. And I say, oh, look, it's a quadratic equation. I should combine like terms, simplify, and write it in standard form, which kind of looks like 12 VE final squared minus 72 VE final plus, I'm thinking that's 96. Now, one thing I notice is that each of these 3 terms are multiples of 12. So I would dearly love to divide everything by 12. Negative 72 divided by 12 is negative 6. 96 divided by 12 is 8. And look, if I told you x squared minus 6x plus 8, go factor that, knowing, let's see, VE final, knowing that one of the roots must be 4, because that was the original value, plus 4. So one of these has to be x minus 4. What's the other guy? Minus 2. And so VE final is either 4 meters per second or it's 2 meters per second. The original value was 4. So we're going to cross this one out and say, okay, VE final is 2 meters per second. Let's go solve the other guy because we're so close to the end of the period. We said 12 equals 3 times the first guy plus the second guy. So that's saying 12 is equal to 3 times 2 is 6 plus the second guy. I subtract 6 from both sides, and I have V final F is 6 meters per second. What does this mean? It means the first guy slows down a little bit. In this case, he drops to half his original speed. But the second guy goes shooting way faster than he was hit. He was hit at 4 meters per second, but he goes flying off to the right at 6 meters per second. Crazy and true. Here is the summary of this particular handout. I suppose what I should do is, if I haven't already posted this handout online, do so. What it says is 3 special cases. If they're identical, head-on, one-dimensional, they exchange velocities. If the moving one is small, it basically bounces with a speed approaching its arrival speed. And the big thing barely moves. If it's a big thing hitting the little thing, like a bowling ball hitting a bowling pin, the bowling ball slows down a little bit and the bowling pin goes flying. Don't believe me? Go bowling. I am now going to stop recording.